Hello everyone. Today I'm going to present our paper titled Eulerian phase-based motion magnification for high-fidelity vital sign monitoring with radar in clinical settings. I am Farhan Oshim. I'm a PhD candidate at the University of Massachusetts Amherst, and this work was done in collaboration with my colleagues Surti, Carreiro, Stephanie, Deepak, Suren, and my advisor, Tauhidur. So the motivation behind this work was efficient and accurate estimation of subtle motions as needed for vital sign estimations are challenging. They are often imperceptible to wireless sensors. So there are a lot of existing literatures with video-based motion magnification, but using a camera is privacy invasive. So we present motion magnification for ultra-wideband radars. It doesn't use any kind of vision. It is wireless, so applications include non-contact, unobtrusive, and continuous detection of target's vital sign. So as a sensor, we use P440 ultra-wideband radar. It operates from 3.1 to 4.8 gigahertz with a center frequency of 4.3 gigahertz. Due to the narrow pulse duration and high update rate, it has a high range resolution, which is actually makes it ideal for subtle motion. In this picture, we can see the ultra-wideband radar antenna. Behind it, we have an absorbent material so that we can make this directional to the front of the antenna. We don't want to pick any signals from behind. Here you can see an Raspberry Pi and hard disk drive. We house everything in a 3D printed box. So this is kind of like a plug and play device which can be used by our doctors without going into technical details. So here we can see the phase-based motion extraction pipeline. Here we have some toy vibrations from pendulum and spring. Also, we have participants sleeping in a different posture. So the whole idea is to get fundamental frequency estimation wirelessly. So from the radar, we get this radar drum, which is a two-dimensional image you can see. On the x-axis, we have fast time or range. In y-axis, we have slow time, or basically the time. The pipeline goes like this. We get this radar drum for our measurements of radar. Then we filter it with the Gabor filter, which are complex wavelets. And these complex wavelets are applied in different scales. You can see different scales from top to bottom. And after the filtering, we compute the amplitude and phase. The phase are then temporally filtered to the desired band of frequencies for the motion. And we amplify those filtered phase with an amplification factor alpha. After that, these amplified phase are multiplied with the amplitude, and we reconstruct it with, again, convolving with the Gabor filters and summing up together with phase alignment, because we don't want any destructive interference. So after that reconstruction, we can see the subtle motions are magnified. So here with the naked eye, cannot see the vibrations, but here we can see the vibrations. So how the pipeline actually works in terms of physics. So we calculate subtle motion like this, fx plus delta t, where f of x is like at t equals to 0, we have a motion f of x. And with a small motion in space, delta t, we can decompose it in an Eulerian manner. So now, in a particular spatial frequency band omega, we can multiply this signal with e to the power I alpha omega del t, which gives us this f of x plus 1 plus alpha del t, which is actually the magnified version. So here, if we can change the alpha, we can get the magnified version of the signal. Now you see, we multiplied with this phase. Now, interestingly, multiplying in frequency domain is convolution in time, and that gives us the opportunity to use Gabor filters, because Gabor filters are basically like this. So here, after Gabor filtering, we do all the processing to get our motion extraction. So we first try with synthetic data, where we have the original scan. At 1 meter, we have a sinusoidal motion, a tiny sinusoidal motion happening at 1 meter distance, which is have an amplitude of only one range width. Each range width is 9 millimeter. And we also have secondary motion at 2 meter, where it does not have sinusoidal frequency, it has a constant reflection. We also have a third motion, a diagonal line, which mimics a person or an object going towards the radar with a constant velocity. So after our going to our motion magnification pipeline with an alpha equals to 10, we can see it is magnified. Alpha equals to 50, it's magnified more. We can also do attenuation with a negative alpha. The application in vital sign monitoring, we collected a lot of data in 3 different settings. The first one is a PNF control setting in our lab with 6 participants with 7 sleeping postures. Each sleeping postures occurred for 5 minutes. The ground truth were collected with biometric t-shirt exoskin. In the second setting was sleep laboratory with 2 participants going through polysomnography for the entire night, so more than 8 hours per night. And also emergency departments where we have 14 participants, each going through 2.5 hours of data collection. The ground truth was cardiopulmonary monitoring quarter-hourly. Now we incorporate machine learning with the features that is extracted from the Gabor filter and motion magnified signals. So here, instead of deconstructing the signal, what we do here is each Gabor filter scale, we do FFT and zero crossing rate. So here, each level, if we have 10 levels of Gabor wavelength filtering, we have FFT and zero crossing. That means n level of Gabor filter give us twice n features. So we use these features to have linear regression with Gabor features and random forest and compare with those with temporal FFT as a baseline. So here are the results. On the left, we have a box plot which shows the respiration rate, phase-based respiration rate, and also heart rate estimations along with the temporal methods for different postures in the control setting. Here we can see that in respiration rate estimation, it's not much of a difference, although we get better results with our phase-based technique. But in the heart rate measurements, we get significant improvements. Also, in the clinical settings, in the sleep lab and emergency department, we have significant improvement with HR estimation. These results are not perfect because we want to consider that these are happening in a situation where there are a lot of background noise, like a doctor or nurse is accompanied with our patients. So a lot of background noise is there. So the temporal FFT does terribly, but we have significant improvement from the temporal methods with our linear regression with Gabor features here, and also with random forest and linear regression in the sleep laboratory. Here we did not collect HR data in emergency department. That was due to some limitations in the emergency department. So in conclusion, what we can say is like we developed Eulerian phase-based motion magnification technique to selectively amplify motions. So previously what we saw here, just I'm going back slides. Here we could see that the motion is amplified in the target, not in the non-sinusoidal noise. So this is one of our achievements, that we can selectively amplify motions, which is specifically useful for vital sign estimation of a target in the presence of limb motion and also secondary person's translatory motion. So this is necessary in situations like emergency departments or like places where there are multiple persons involved. We did feature extraction from the motion magnified signal and also use machine learning models to respiration and heart rate estimations that resulted in greater accuracy. We also validated in the clinical settings. So in future, what we want to do is like you gather more data to have a more generalized pipeline with deep learning features, deep learning techniques, so that it can be generalized to more diverse environments. That was all. Thank you for listening. If you have any questions, I'm happy to answer. You can also contact me through my email and also visit our lab website, mosaic@cs.edu.